Alright, so in the last video, uh, we talked about how x plus y to some power z will produce different things based on what z is. So if z is 1, it's just going to produce x plus y. So x plus y to the 1 is just x plus y. If z was 3, if z was 3, then we would get x cubed plus 3 x squared y plus 3xy squared plus y cubed, and so on. Anyways, these coefficients for each of these terms can be represented, sort of represents the combinations that x's and y's can be chosen. And I talked about that, I explained that in the last video. But I'll just talk about it briefly. So we know that x plus y cubed is x plus y. So I'll just talk about it briefly just to recap. But anyways, let's start talking about it. X plus y cubed is this, right? It's x plus y times x plus y times x plus y. Now, each of these factors, so these are our three sort of factors that are being multiplied together to equal this, can either be sort of an x or a y. So what I mean by that is when we're multiplying these together, for example, maybe this is an x, this is a y, and then this is a y. And that would produce x times y squared. Okay? Now, so that would produce x times y squared. Now, there are a certain number of ways that x's and y's can be chosen from these three factors. So for example, maybe this first x isn't chosen. Maybe it's a y that's chosen from this first factor, and then an x that's chosen from the second factor, and then a y that's chosen from the last factor. That will also produce an xy squared, but in a different way. So when we're multiplying these x plus y's together, we know that all possible combinations of x's and y's will be multiplied together. Okay, it will happen. So for example, x times x will happen, x times y will happen, y times x will happen, y times x will happen, y times y will happen, and then from that, all of that will be multiplied by this x plus y, and overall we're going to end up getting all of our combinations. So we're going to get all of the different possible ways we can produce xy squared. We're going to get x cubed, because that's possible if we choose x for all three of them, right? X times x times x is x cubed. We're going to get a y cubed, because that's possible if we get if we pick y from all of them, y times y times y. But there's only one way to do x cubed. There's only one way to get x cubed, only one way to get y cubed, because that means that either they're all going to have to be x's, or they're all going to have to be y's. Anyways, so all of these combinations will happen when they're being multiplied together. So yeah. So if this can be either an x or a y, maybe this is an x, then this is a y, then this is an x, that's going to produce an x squared y. Okay? That's just one of the ways to make an x squared y from these. It could switch order. Maybe this one is an x, and then maybe they change orders, right? Maybe different ones are x's and different ones are y's, right? So there are different ways to produce different terms. So this x squared y, there are actually three different ways that x squared y can be produced, and that's shown by the coefficient. The fact that there are three x squared y's when we multiply x plus y cubed together suggests or proves that, or sort of says that there are 3 combinations for picking 2 x's and 1 y out of these 3. So maybe you could pick x here, then y here, or maybe you could pick y here, x here, and then x here, right? And so on. There are a bunch of different ways to do it. Or there are 3 different ways to do it, in fact. So like I said before, all possible combinations will happen. So these coefficients sort of represent the number of combinations in this case, 2 x's and 1 y can be chosen. Or if it was 3xy squared, 1x and 2 y's can be chosen. That's what these coefficients sort of represent. Because that's the number of x squared y's that were produced. So for example, for this, there's a 3. That means that 3 x squared y's were produced when all of the combinations were tested and added together, right? So all of the different combinations. So we could have gotten an x, a y, and a y. We could have gotten a y, an x, then a y. All of those types of combinations, in general, those general combinations, will produce different terms, but the coefficients represent how many different ways those terms can be made. So for example, the 3 here represents how many different ways x squared y can be made. Or in other words, how many different ways 2 of these can be x's, and then only 1 of them can be y's. But I think I went into more detail in the last video. So if that was not clear enough, you can go back to the other video, and if that isn't clear either, you can go to Khan Academy, or if you're doing this in school, use your schoolwork. Okay. Anyways. So we've established that these coefficients represent the number of different ways certain terms can be produced. So for example, x squared y, there are 3 different ways x squared y can be produced from x plus y being multiplied by itself 3 times. Okay. What if we had x plus y to the 4th? Right? Well, we know that, well actually let's just draw out all of these x plus y's. There are going to be 4 of them. Okay, what sorts of combinations of x's and y's are we going to get? Well, let's think about that. We could have 4 x's, right? It's possible that we could just pick an x from every single one. And how many different ways can that happen? And you can pause the video and think about that. I'm just going to answer. There's only one way that can happen, because that would mean that all of them would have to be x's. So this one would have to be an x, this one would have to be an x, this one would have to be an x, and this one would have to be an x. What else are we going to have? Well, we could have 3 x's and then 1 y. Just write plus. We could have 3 x's and then 1 y. So we would have x times x times x times y. How many different ways can that happen? Well, the number of ways that 3 x's and then 1 y can be chosen is the same as the number of ways one of these can be chosen to be a y, right? Because we know that only one of them is going to be a y. How many different ways can one of these be a y? Well, this one can be a y, or this one can be a y, or this one can be a y, or this one can be a y. So there are 4 different ways because there are 4 different options of x plus y's to be y. So there's going to be a coefficient of 4 there. And we're sort of seeing that we're able to get these coefficients from the combinations. What about x squared, y squared? Well, we can use similar logic that we used in this one, in this example, in this one. We can just say that's the same. The number of ways to get 2 x's and then 2 y's is the same as picking 2 of these to be y's. So we're going to pick 2 of these to be y's. How many different ways can 2 of these be y? Well, that's the same as finding out how many different ways we can pick 2 x plus y's out of this group. So we're going to randomly pick 2 x plus y's out of this group, and we're going to find out how many different ways we can do that by picking the different x plus y's. So maybe we could take this one and then this one, right? Or maybe we could take this one and then this one. So there are a bunch of different ways to do that. And if you remember from our combinations, the way to do that is actually to draw 2 positions, right? Or this is just for visualization purposes. You don't have to draw 2 positions. But we could take 2 out, right? We know we're taking 2 out. So what the first one can be 4 different things, right? The second one can only be 3 different things, right? Because it can't be the first thing. Now this would get the number of permutations for picking out 2 x plus y's, but we only want combinations, so we would divide it by 2. So we would get 6. There are 6 different combinations for picking out 2 y's, and therefore there are 6 different combinations for picking 2 x's and then 2 y's. So I was pretty brief about that because we have done videos on combinations. If you need a recap on that, or you have never heard of combinations, then you can go to my combinations video, or also you can go to Khan Academy, or if you've done combinations in school, you can look back on your schoolwork for combinations. Okay, so we know that we would have a coefficient of 6 here because there are 6 possible ways we just discovered of picking 2 x's and 2 y's. Okay. How many different ways can we get 1x and 3 y's? Well, that's the same as finding out how many different ways we can pick one of these to be an x, right? How many different ways can we pick one of these to be an x? Well, this one can be an x, this one can be an x, this one can be an x, or this one can be an x. It's the exact same logic for this one over here, except instead of y, we're saying one of these can be an x. So there are 4 different ways. Then we're also going to have y to the 4th, and there's only one way for that to happen, because that would mean that all of them have to be y's, and there's only one way for that to happen. Yeah. Okay. So we pretty much established that we can find out the coefficients for these different terms by using combinations. Now I want to use combinations to make a formula sort of to represent what these x plus y to some power z's will look like in general. Okay, so x plus y to some power z will equal, what will it look like? Well, it will look like x to the z, okay? So just like x plus y to the 4th will produce an x to the 4th, x plus y to the z to any power will produce an x to the z. And how many of those will there be? Well, there will always only be one, because there's only one way for all of these x's to be, for all of these factors to be x. So yeah, so we're always going to have some x to the z. If we were to have x plus y to the 5th, it would produce an x to the 5th, just one, okay? Now it will also produce an x to the z minus 1 and a y to the power of 1, okay? So it's possible that all of them are x's except for one of them, which is a y, right? So it might be kind of hard to think about because it's in general and we're using variables, but really this is the same as this. Just like for x plus y to the 4th will produce an x cubed and a y, this will produce an x to the z minus 1 and a y to the 1, right? Because it's possible for all of them to be x's except for one, which is a y. So let me just say, let's say x plus y to the fifth. Let's use that as an example again. It's going to produce an x to the fifth, we just said that, but it's also going to produce an x to the fourth times y to the 1, right? Because it's possible that 4 of these x plus y's are x's and only one of them is a y. So this applies in general for all x plus y to z's, except we have to say z minus 1 and 1 instead, just to keep it general. Because, for example, if it was x plus y to the 6th, it would be x to the 5th times y, right? Or if it was to the 100th, it would be x to the 99th times y. So on. Okay. And this would keep going on. We would be able to have x to the z minus 2 and y squared. Okay, so it's possible for 2 of them to be y's and the rest to be x's, and so on. And then this would continue on until we had x squared times y to the z minus 2. So now we have all of them are y except for 2 x's, and then we have all of them are y except for 1 x. X to the 1 times y to the z minus 1. So just like there's a y cubed times an x, there's going to be a y to the z minus 1 times x. So it's possible for all of the factors to be y's except for x. And then plus y to the z. So it's possible for all of them to be y's. Okay, so those are the different sort of terms that are going to be produced by x plus y to the z. But we're not quite done yet, because we know that each of these terms is going to have a coefficient, right? There is a certain number of ways that each of these terms can be produced. So for example, x to the z, we know that there's only going to be one way to produce that, right? But that's an easy one. For example, x to the z minus 1 times y. How are we ever going to predict that? Well, it turns out there's a way that we actually can predict that using combinations. So let's say we have x plus y to the fifth. Okay? We know it's going to produce x to the fifth. We were talking about it earlier. And it's also going to produce a certain amount of x to the fourth times y's. Some number, right? But we don't know what that is yet. So let's calculate that number. Well, how many different ways can y be chosen from 5x plus y's? Well, there are going to be 5 different ways, right? Because there are 5 different ways to choose one x plus y from the group. So if we have 5 x plus y's, 5 of them, then we choose one of them to be a y, right? And then the rest would be x's. We want to find out how many different ways we can do that. Well, there are going to be 5 different ways to do that, because we can pick any of the 5 x plus y's to be y, right? So I'll write it all out. X plus y, x plus y, x plus y, x plus y, and x plus y. Any single one of these can be a y. So this one can be a y, maybe, or this one can be a y, or this one can be a y, this one can be a y, this one can be a y. So any of the 5 can be y's. So any of these 5 x plus y's can be y. So the coefficient is going to be 5, because there are 5 different ways to pick out 4 x's and then 1 y. Because there are 5 different ways to pick out one of these x plus y's to be y. But that's only for this case, right? We need to find a way to generalize this. We need to find a way that we can apply this to our general sort of formula, right? Well, if you remember from last video, I think, I talked about notation. Okay. Actually, that doesn't look... Okay. So this is a z, and then this is a 1. Okay. I'll get back to what this is in a second. I just wanted to write it out. But I'll talk about that in a second. But anyways, I was talking about notation. If we were to write a C and then, let's say, a 4 and then a 3, if you remember from last video, that means that we have a combination situation or a combination scenario where we have 4 different things, 4 different elements, right? We call them elements, and then we find out how many different combinations, so number of combinations, so number of combinations to pick out 3 of these. Okay, that's what 4 choose 3 means. This 4, and then a C in the middle, and then a 3. That's the number of combinations for picking out 3 elements from a 4-element group. Or for example, C, 3, and then 1. That's how many different ways we can pick out 1 element from a 3-element group, and so on. If you remember from last video. If not, you can go back to that. It's at the beginning of that video, I'm pretty sure. And if that doesn't make sense, you can go to Khan Academy, or if you've done this in your school, you can go to your schoolwork. But that notation can be used and it can be generalized. Actually, let me just... Okay. And I wrote this z choose 1 earlier, right? And what I mean by that is whatever z is. So let's say it was 4, right? If it was 4, that would be c 4 choose 1, right? So we're finding out how many different ways we can pick out 1 from 4. Okay? So this number of combinations really depends on what z is. So in this case, how many different ways can we pick out 1 of these to be y, right? Well, 5 choose 1, right? Because there are 5 elements and we have to choose 1 of them to be y. In the x plus y to the 4th case, it's 4 choose 1, right? So depending on whatever this exponent is, it's going to be a different number of combinations for this second term. So this second term's coefficient is going to have a different number of combinations depending on what this exponent is. So let me just recap to make sure that makes sense. This x plus y to the 4th, the coefficient of its second term, where we are picking one of the x plus y's to be y, is 4 choose 1, right? For x plus y to the 5th, it is 5 choose 1. And it keeps going like that. Depending on how many x plus y's we have multiplied together, we know that we need to pick one of those x plus y's to be a y, right? So if we have z x plus y's, and we need to pick out one of those x plus y's to be y, the number of combinations for doing that is z choose 1, where z represents however many x plus y's there are, or in other words, whatever the exponent is. Okay? So the coefficient here, and I'll actually just make some space, the coefficient here is z choose 1. So that's the coefficient, z choose 1. And that's how many x to the z minus 1 power times y you are going to have. That's how many of those terms you are going to have. That's how many possible ways you can pick out y from a certain number, from z amount of x plus y's. Okay? Yeah, so I'll just recap because that was a lot of talking, and just in case I missed anything. there are zx plus y's, and we want to pick out one of those x plus y's to be y, right? One of them is going to be y. So if one of them is going to be y, then we know the number of combinations for choosing one of them to be y is going to be z choose 1. Because we know we're always going to be choosing one of them to be y, right? And we know that we're picking it out from z amount of x plus y's, right? Depending on whatever the exponent is. So that's how we generalize it. We say that it is z choose 1 for in this case. Now what about this next term, right? What if we were picking out two y's? Well, that's the same as saying how many different ways can we pick y twice? Well, that's just going to be z choose 2, because we're picking two of those x plus y's to be y, right? We're choosing two of them to be y, right? And what if we had, I don't know, well, let's say I didn't skip this. Let's say x to the z minus 3 y cubed. What's the coefficient for that? Well, it would be z choose 3, right? It would be z choose 3. Because you're choosing three of the x plus y's to be y, right? And then the rest will be x's. So we want to find out how many combinations we can do that, and then that is going to be the coefficient. So let me actually just write these coefficients in, clean it up a bit. Okay. This will be z choose 2. Z choose 2. That's the coefficient here. That's how many different ways it's possible to pick out two y's, or in other words, that's how many different ways we can pick out z minus 2x's and 2 y's, and so on. Each of these will have different coefficients. Now what about when we get to the end here, right? Well, how many different ways can we pick out z minus 2 y's from a group like that, right? If we had like a bunch of x plus y's, we have a bunch of them, right? Dot, dot, dot. And then we have more x plus y's, right? We have a bunch of them. And we wanted to pick out z minus 2 of them, so all but 2 of them, to be y's. How would we do that? Well, we would just write that as we have z in our initial group, right? We have z elements in our initial group. That's how many x plus y's we have. And we know we need to pick out z minus 2 of them to be y's. So that's going to be our coefficient for that as it nears the end. And you might be able to guess what this one is. Just make some space. It's going to be z choose z minus 1, because we're choosing all but one of those x plus y's to be y. Okay? Now, so again, we're just choosing all but one of those x plus y's to be y. And the number of ways we can do that is written as 2 choose z choose z minus 1. By the way, this is just notation for, you know, writing a number to represent a number of combinations to do something. Actually calculating the combinations we talk about in previous video. We talked about in previous videos. So for example, if you had 5x plus y's, or 4x plus y's, let's say, 4x plus y's, and we want to pick one of them to be y, we talked about how we could do that in past videos. I won't talk about that now. And if that is confusing, if you go back to my combination video that's confusing, you can go to Khan Academy, or if you've already done it in your school, you can look at your schoolwork. Anyways, as I was saying, yeah. So, and also, I know I said that there is just going to be a 1 as a coefficient for x to the z, and a 1 as a coefficient for y to the z. But those 1s can also be written as z choose 0 and z choose z, respectively. Okay? So, if you really think about it, there are going to be 0, if you want x to the z, right? X to the z. I'm talking about x to the z right now. If you want to only get x's, you need to find out how many combinations there are where you get no y's. So you're picking 0 y's out of z elements. So you're picking 0 of those elements out of z elements, right? And that actually is equal to 1, but it can sometimes, we can just write, we can just write that over here. Z choose 0. As the coefficient for x to the z, it's equal to 1, right? It's equal to 1, but we can write it like that. If you think about it, it's equal to 1 because you're finding out how many different ways you can take out 0 of those x plus y's to be y. And there's only one way to do that, because that means that they're all going to be x's. Y to the z, that's how many different ways we can pick all of them to be y. There's only going to be one way for that to happen, right? So we're picking all of them to be y. So from z elements, we're picking z of them to be y, right? So all of them to be y. There's only one way to do that, because that means that they're all y. You can imagine there's only one way to do that. Whoa. Okay, let me just fix that. Okay. So there would only be one way to do that, because there's no other way to recombine those. There's only one way to pick out all of them, right? Okay. So what was the point of doing all of that, right? Like, how can we apply this? Well, when we're actually putting x plus y to some z power, we might want to know the coefficients of those different combinations. Of those different terms. So I'll make some space over here. Let's say we had x plus y to some power z, okay? Or actually, let's say we had x plus y to some power 100. The 100th power, right? And that's pretty daunting. You're not going to want to write all of that out, right? And if you wanted to know maybe there was some number x to the 17th times y to the 83rd power, right? And we know that there's some coefficient here, but we don't know what it is. If we wanted to find that out, how would we solve that? Well, we can go back to our formula over here, and we can realize that all of these coefficients are just combinations. We can look at all of these coefficients and just realize they're combinations. And in this case, what would the coefficient for this be? Well, we know that it's 100, so C, and we write out 100 here, right? And then whatever the y exponent is. So I forgot to mention this, but down here in the formula you see for all of these combinations, you notice it's z choose 1 when y is to the 1 power, z choose 2 when y is to the 2 power, z choose z minus 2 when y is to the z minus 2 power. It's whatever the exponent is for the y, because that's how many y's we're picking out, you can imagine. But anyways, in this case we're picking out 83 y's, so it would be 100 choose 83. By the way, when I say 100 choose 83 or like 4 choose 3, that's just how I say it. I say this number first, then choose, then this. But that's what I mean. That's what I'm talking about when I say that. But anyways, we found out that it's 100 choose 83. So how many different ways can we choose 83 of those x plus y's to be y, right? Well, let's just think about our formula, our combination formula. So I'm just going to use the combination formula. I'm just going to assume you know it. If you don't, you can go to my combinations and permutations videos, and if that doesn't make sense, then you can go to Khan Academy, or if you're doing this in school or have done this in school, you can look at your schoolwork. Anyways, so we're going to take the number of elements in your initial group, then you would divide it by the number of elements in your initial group minus the number of elements you're taking out, factorial, and then you would also divide it by the number of elements you're taking out, factorial. Okay, and that actually turns out to be 6.650. I just used a calculator. 1349 times e to the 18. So that's a really big number. That basically means it's times 10 to the 18th. So that's in other words times 10 to the 18th. Sorry, I shouldn't have said e to the 18th. I meant that's how it appears on your calculator, but this is what it means. When you see 6.6501349, e to some number, e and then some number, that means that it's that number multiplied by 10 to that power, to the power of that number. Not to confuse you about e, which is actually something, a different number entirely. So it's I won't get into it, but yeah. So the point is, that is our number. It's really big. You can imagine you wouldn't want to have to write out everything to find out what the coefficient was, or how many different ways you can get 17 x's and then 83 y's. But anyways, that's our coefficient. Yeah. So that's sort of the application of this formula. And it's important to note that this formula isn't just cannot only be applied isn't only applied to x plus y to some power. It can also be applied to other binomials to some power. So like, I don't know, 2x plus 1 over y, right, to some power z. That would just be written as z choose 0, right? Instead of x, we have 2x to the z. Sorry, that looks like a 2. That's a z. Some of my z's look like 2's. And then it would be z choose 1 of 2x to the z minus 1. times, well, I guess it would be 1 over y to the 1. So you can see we're just, instead of x's and y's, we're just plugging in 2x and 1 over y. And then that would go on the same way the other formula does. So it can be applied to, actually, let's just keep it there. It can be applied to other binomials to some power as well, right? Okay. An example of it being applied to something like that would be if maybe you were given 2x plus 1 over x squared to the power of, I don't know, 3? Yeah, sure. And you were asked to find out the number that does not have an x in it, okay? So it doesn't have a variable in it. Now this might seem kind of scary at first, but really all you have to do is you have to find a term where you have the same, or where you have enough 2x's to cancel out with the x squareds. So for example, 4x squared divided by x squared would just be 4, right? So these would cancel out. And I'll actually just give away the answer for this one. It is exactly what I just wrote. It's 4x squared. So in other words, you have two. You picked 2 of the 2x's, right? And then you got 1 of the 1 over x squareds. And I didn't write the coefficient for that, but all right. But you can kind of imagine if you picked 2 of these, so I'll write it all out, 2x plus 1 over x squared times another 2x plus 1 over x squared times another one, let's draw it over here, 2x plus 1 over x squared, right? Maybe you, for any of these where you pick 2 of them to be 2x's and 1 of them to be x squared, that means that the x's will cancel out. So that's how you would answer that question. You would find out what number of 2x's you need and what number of 1 over x squareds you need in order to get a term where the x's cancel out. And what you need is 2 2x's and then 1 over x squared. And if the question was, what is the coefficient for that, you would have to find out how many different combinations there were for picking out 2x squareds, 2 2x's, and 1 over x squared. And how you would do that is you would find out how many ways you can pick out 1 over x squared from this from these three 2x plus 1 over x squareds. So basically, how many different ways can you pick one of these to be 1 over x squared? Well, 3, right? Because you can pick any 3 of those to be 1 over x squared. So you would have a coefficient of 3. So you can answer the question by saying the coefficient for the term that does not have an x in it would be 3. Okay. So just to recap that question, you would have to find out what number of 2x's and what number of 1 over x squareds combined, assuming that you can only have 3 total, right? So you can have like 2 2x's, 1 over x squared, right? You can only have 3 total, or you could have like 1 2x and then 2 1 over x squareds. You know what I mean? And then you could have 3 2x's or 3 1 over x squareds. So these are our four sort of scenarios for different numbers of those things. Let me just make that 3 a little bit less close to the 2. Right? Okay. So any of those, and you would need to choose the one that has it where the x's cancel. So there are two 2x's here and one over x squared. So because there are two 2x's, we get 4x squared, and the 4x squared and the 1 over x squared, they cancel. The x squareds cancel, at least. And that makes it so that there are no more x's. And that would be our term with no x's. And then you would need to find out the coefficient for that using combinations. You wouldn't actually have to write them all out to find out which one has x's that cancel, by the way. You can also just find out how many x's there are over here, how many 1 over x squared, how many 1 over, well in this case, how many 1 over x squareds there are here. And you would need to find out a combination of the two where, well, in this case, we know that there have to be 2 times as many of these as these over here, right? So there need to be 2 times as many of these as there are of these, okay? So just one more time, 2 times as many of these as there are of these, because there are x squareds over here and only x's over here. So there need to be twice as many x's to cancel out 1x squared. So 2 x's to cancel out 1x, over 1 over x squared. Yeah. So I'm just going to recap one more time for that problem, for that question. We had a binomial where there was one term that had a positive exponent, so x, right? And then we had another one where the exponent on the x was negative, so we had 1 over x squared. And we needed to find out a way to cancel those two with each other. We needed to find out which term had the right number of 2 x's and 1 over x squared so that they would cancel. The way to do that is basically find out how many of one you need to cancel out with the other one. So for example, in this one, I said you need 2 of these to cancel out with 1 of these, and therefore you need double the amount of these as these. And the only way that's possible is if you have 2 of these and 1 of these, because there can only be a total of 3. Let's see. If it was 6, if it was 2x plus 1 over x squared to the 6th power, let's say it was to the 6th power, then we would say that we need 4 of these, and then we need 4 of these, and then 2 of these, because we need to satisfy the condition that there are twice as many 2x's as there are 1 over x squareds. If there were, I don't know, if it was x cubes instead, okay, and it was to the power of 4, let's say, we would know that we need 3 times as many of these, right? Because we need 3 of these to cancel out with 1 of these, so there need to be 3 times as many of these as these. So the only condition we can have for that is if we have 1 of these and 3 of these, and that where the total is 4. Yeah. So that's just recapping. Let's go back to our original question. Okay. Yeah. You might also, let's just do one more question as an example for what you might come across. There are a lot of different types. These are just a few that I'm showing you, just to give you a feel for what you might run into. Let's say you had 2x plus y to the 4th, and you were asked coefficient for the coefficient of of the third term. Okay? So we would know that the coefficient of the third term, right, would have y choose 2, c choose 2. It would be z choose 2, right, because we know the first term would be z choose 0. The second term would be z choose 1. So the third term would be z choose 2, right? So this is what we need to figure out. And we know that z is 4, right? In this case. So I'm just going through this question. I'm not going to, but I'm not going to, explain as I go. I'm just going to do this question. But anyways, we basically we know that we have to choose 2 because that is going to be the third term in any of these formulas, right? In any case where we're putting a binomial to some power, right? Anyways, oh, by the way, yeah, this is really important. This formula can only be applied to binomials. If that wasn't, if I didn't make that clear. But anyways, we know that it's going to be z choose 2, or in other words, it's going to be, in this case, 4 choose 2, because we know that we have, it's to the power of 4, right? And then we would just calculate it out. So we would say 4 factorial divided by 4 minus 2 factorial times 2 factorial, right? And that would just get us 1, I think. No, it wouldn't. Let's see, 4 times 3 times 2 is 24, divided by 4 is 6. Okay, so there would be 6 different ways of getting the third term, right? 6 different ways. So in other words, the coefficient of the third term is 6. So that's how you would solve that. That sort of question. So those were just a few of the types of questions that you might run into. But they all involve applying this formula that can be used on binomials to different exponents, right, with different exponents. They all involve the use of this formula. Okay. Anyways, that pretty much concludes this video. Thank you.